Welcome to the Explainer. Today, we're going on a really fascinating, multi-layered journey into something your body does so seamlessly, you probably take it completely for granted: repairing a simple scrape. But as you'll see, beneath the surface of an everyday healing scab lies an incredibly complex, microscopic battlefield. We're going to explore this whole process by looking at the biological timeline, breaking down the actual differential equations that predict healing success, and finally, looking at the systemic nutritional fuel that you actually control. To understand why this science is so absolutely crucial, let's look at the real-world stakes. 9,060 euros. According to a recent study, that is the staggering average annual cost to care for just one chronic wound in Germany. When the body's natural healing equation breaks down, it's not just a biological failure, right? It becomes a massive systemic and financial burden. Across the globe, literally billions are spent trying to fix wounds that simply refuse to close.
So the crucial point is understanding the fundamental difference between an acute wound and a chronic one. An acute wound normally progresses right through its healing phases and closes up in about 3 weeks. A chronic wound, however, gets totally trapped. Whether it's due to diabetes, an infection, or just poor nutrition, it gets stuck in one specific phase of the healing process and just fails to respond to treatment. To prevent a wound from going chronic, we really have to understand exactly what those phases are.
So here's our roadmap for today. 1. Anatomy of a wound. 2. The cellular construction crew. 3. The math of healing. And 4. Fueling the fight.
All right, let's jump right into section 1, anatomy of a wound and its timeline.
Okay, let's dive into this. The wound healing process happens in 4 overlapping chronological stages. Stage 1 is hemostasis, which happens right away in the first 24 hours. Think of this as the emergency response. Blood vessels constrict, and platelets trap together with fibrin to form a clot. Next up is inflammation, lasting from day 1 to 7. This is when your body is hard at work clearing out damaged cells and bacteria. Then we enter proliferation, from day 4 to 24, where new tissue and blood vessels are actively being built. And finally, remodeling. This starts around day 14 and, believe it or not, can take up to 2 whole years. This is where the new tissue is organized and strengthened. So that's the timeline for our cellular construction site. Moving on to section 2. Let's zoom in and meet our microscopic actors, the cellular construction crew. Meet the absolute protagonists of our story, fibroblasts. These are your essential builder cells. When a wound happens, fibroblasts proliferate, they migrate straight to the injury site, and eventually they become activated. Once they're active, their main job is to produce collagen. If fibroblasts are the construction crew showing up in microscopic hard hats, while collagen is the brick and mortar. The actual physical strength of your healed wound is entirely dependent on the quantity and quality of collagen that these fibroblasts secrete. But fibroblasts don't just work in a vacuum. In this mathematical model of the microscopic battlefield, we see that the initial wound invites pathogens in. In response, your body sends inflammatory cells. Think of these inflammatory cells as the security guards. They are totally vital for destroying those pathogens. But notice how they also interact with the fibroblasts. In this chaotic environment, inflammatory cells can actually accidentally destroy your own fibroblast builders. It's a super delicate, nonlinear balance. You need enough inflammation to clear the infection, for sure, but not so much that you end up killing off your own construction crew. Which brings us to section 3. Let's look at the math of healing and the variables of success. And this brilliantly illustrates how local factors totally alter the math. When oxygen levels drop below a critical threshold, the pathogen growth rate spikes drastically. At the exact same time as oxygen drops, the ability of your inflammatory cells to fight back just plummets. So a lack of local oxygen simultaneously arms the enemy and cripples your security guards. It's basically a microscopic worst-case scenario. To figure out exactly what helps or hurts our fibroblasts the most, researchers use something called a global sensitivity analysis, which is visualized here as tornado plots. We don't need to get bogged down in the complex statistics, though. Simply put, the blue bars represent factors that act like a gas pedal, speeding up our construction crew. The orange bars, those are the brakes, representing factors that slow them down. For example, high pathogen growth and inflammation show up as massive orange bars, heavily correlating with decreased fibroblast activity. On the flip side, the rate of collagen production is this huge blue bar, giving our builders the ultimate biological speed boost. Now, what's really interesting about this slide is this single mathematical threshold, denoted as RW. For a wound to fully heal, what mathematicians actually call a wound-free equilibrium, this RW value has to be less than 1. When researchers analyzed what impacts this threshold the most, one factor stood out with the largest negative correlation: meaning it drives the number down and speeds up healing. And what was it? The density of collagen at the wound-free equilibrium. Mathematically speaking, stimulating collagen activity is the ultimate key to expediting the entire healing process.
So we've seen the timeline, and we've looked at the mathematical models proving that fibroblasts and collagen are the real heroes here. But we don't live in a computer simulation, right? So how do we, in the real, macroscopic world, systemically fuel this cellular construction crew to guarantee they win the fight and achieve that wound-free equilibrium?
That brings us to our final section, fueling the fight through systemic nutrition. Let's start with amino acids, the literal building blocks for tissue repair. Arginine is absolutely vital because it's a direct precursor for producing collagen. But there's a catch here. Supplementing arginine only works if the patient has sufficient overall protein in their system. Otherwise, it's completely ineffective. Then we have glutamine. Remember how dangerous out-of-control inflammation is to our fibroblasts? Well, glutamine acts as an antioxidant and plays a huge role in regulating that inflammatory stage, protecting the wound from infectious complications.
Next up, let's look at how vitamins build on this process. Vitamin A stimulates fibroblast activity and epithelialization. It's actually so effective, it's often applied topically. The B vitamins act as vital cofactors to manufacture collagen. And vitamin C? That's required to cross-link and stabilize the collagen matrix, which is what makes the new tissue really strong. But look closely at vitamin E. While most vitamins are entirely beneficial, studies show that vitamin E can actually have adverse effects on the inflammatory phase. It can even mitigate the healing benefits of vitamin A. So yeah, more is definitely not always better.
Finally, we have minerals, specifically zinc. When a wound happens, cells like our fibroblasts and those inflammatory security guards have to divide rapidly to respond to the trauma. This cellular replication requires DNA replication, and zinc is a mandatory structural component of the enzymes that do this. Without zinc, that mathematical multiplication rate of fibroblasts we saw in the earlier models, it simply grinds to a halt.
So, what you should really take away from this explainer is that healing isn't just something that passively happens to you over time. It is a highly delicate equation. You need the local cellular activity of fibroblasts balancing perfectly against inflammatory cells. You need adequate oxygen to suppress pathogens. And crucially, you need systemic nutrition, the proteins, the vitamins, and the minerals to serve as the literal biochemical fuel for the whole process. If any part of this equation fails, a simple acute wound risks becoming a chronic nightmare. Every cut, scrape, and surgical incision turns your body into a marvel of mathematics and biological construction. And the amazing part? You are in control of the supply chain. So the next time you get a simple paper cut, what will you feed your cellular construction crew? Thanks so much for joining me on this explainer, and keep learning.